Hi, and welcome to the eighth lecture on my series on Introduction to Quantum Theory and Technologies. This time we're going to be talking more about basis rotations. So this is something which is actually very sort of fundamental to quantum theory, but actually happens in any kind of vector kind of system. So if you are already familiar with vectors, then you might already be fairly familiar with this kind of idea. But in quantum theory, it's sort of, it looks a little bit different. So let's just sort of go through by first, um, let me introduce it by first talking about a system that's like, nothing got to do with quantum mechanics. Um, in general, we can always use different coordinate systems, and we're basically free to choose our coordinate system according to basically our own kind of convenience. And the coordinate system is just basically some system that you set up that basically it's just a convention. It's a bit like, there's no particular reason that we uh, say that basically the North Pole is like, the basically the top of the Earth and the South Pole is the bottom. The equator is in the middle, or, the Greenwich Mean Time is the standard definition of basically, the 0th hour of how time is calibrated. I mean, these are all just basically conventions that you can use, and you could use a different convention, but you need to sort of agree on a particular convention. But apart from that, the particular convention that you use is not particularly important, right? So this is the idea of sort of coordinate systems. So just to illustrate this, let's just look at this sort of simple example. So here's Alice and here's Bob. So often in quantum information, we have these two people, Alice and Bob, and sometimes it becomes Charlie and Dave and so forth. The most important thing is that their names are beginning with A and B is probably the most important things, right? So basically we have Alice and Bob, just two people, and they're looking at some plane that's flying in the air. So it's obviously flying in some direction, some velocity. And basically, depending upon the direction that they're facing, well, obviously, they'll see the plane move in different directions. So, for this guy, it's kind of moving relative to him. It looks like it's going forward, like, in front of him. Whereas for Alice, it's kind of flying over the top of her head and kind of going backwards. And obviously, because they're standing in different directions, right? So, relative to what they are seeing, Alice and Bob, the plane is going in different directions because they're facing different directions, right? So, this is a perfectly obvious thing. Alice and Bob sees the plane move in different directions relative to them since they're facing different directions. So, well, duh, right? So, um, uh, basically the plane has some reality, right? So this vector is obviously the same thing, you know, just because Bob and Alice are different people viewing it doesn't, change the nature of it. This is the kind of reality of what the plane is doing. And what's actually changing is just your kind of relative perception of it and how you describe it. Another way to sort of put this in more physics terminology is that Bob and Alice have different coordinates, and so they describe the movement of the plane in different ways. Okay, so perfectly obvious kind of fact, right? So in quantum mechanics, we have exactly the same thing. So we have quantum states that are described by different vectors. And so here's a particular example of some quantum mechanical vector. And before we said that each of these states here, like the 0, 1, up to n, are different or distinct states of the physical system. So just, examples are like, so some electron, it goes left or it goes right. These are different states. Or in an atom, there's different energy levels, some high excited states or some lower ones. Whatever it might be, these are different distinct states of the physical system. So in the language of these, coordinate systems or the, linear algebra, these 0, 1, 2 are actually the basis vectors, or, basically your coordinates that you are kind of setting up here. So the 0, 1 here are like these coordinates, but we could have chosen some other set of coordinates, and we could equally describe the same state, right? Just like Alice and Bob are looking at this plane, it's the same plane moving in some directions. They just got a different take on basically the direction of movement of the plane. So in the same way, in quantum mechanics, we can have a different take on the same state, exactly the same state, just a different way to represent that state, right? So, for example, Bob, say this was the choice of Alice, right? Alice says, okay, I'm going to represent my quantum state in this way. Bob could also just say, well, no, I don't want to choose that convention. I want to choose a different convention. I want to choose different set of basis states. Let me label Bob's choice by a little b here. Say these guys are the original Alice's ones. This is Bob's. So Bob's choice are these ones with the B's. And of course, because Bob's chosen a different convention, different coordinate system, he's going to get different coefficients, right? So these B's are going to be different numbers to the A's, right? But it's exactly the same state because just, as I said over here, it's just a different coordinate system, different way to represent it, but the actual object is still the same. So when Bob chooses these basis states, what we're going to use here, you don't actually have to, but what we're going to do here, just for sake of simplicity, is that all these states here, like the 0, 1 to n, are all like orthogonal vectors, just like they were up here. So over here, we assume that all these kind of basis vectors here, the 0, 1 to n, were all orthogonal, and they were all normalized. Bob also should choose that in the same way. Okay, so let's just look at a particular example here, just so that you sort of get the feel for this. So, for example, let's say that Alice had a state, and it was in some arbitrary state, alpha 0 and beta 1. Okay, that was one way to write the state. But we can actually write it in another kind of basis, another coordinate system, right? So Bob can represent the exact same state using the basis vectors written like this. So this is not the only choice that Bob could have made, but this is just one example. And it's a pretty common example, so we'll be coming back to this. This is a good way to introduce it. So Bob, suppose we define these two states, this so-called plus state and the so-called minus state, okay? So I'm going to define it like this. So 0 plus 1 times square root of 2. Just make sure it's normalized properly. The minus state has minus sign. So what are these states? Well, we can visualize it here. If 0 and 1 are these orthogonal vectors, the plus and the minus states are these states which are like at 45 degrees to each of these axes. The minus state is also minus sort of 45 degrees to this axis. Here's our state psi just pointing in some direction. And these and what we're going to do is we're going to try and rewrite this state in terms of the plus and minus basis convention rather than the 0 and 1. Okay, so that's what we're going to do. But first, let's just check that these vectors that Bob chose are actually orthogonal, because we want them to be orthogonal. These were orthogonal, the 0 and 1, you know, the inner product is 0. And we also want them to be normalized properly. Okay, so for example, let's just check firstly that this one is normalized. So let's look at the inner product of plus with itself. That tells us like basically what its length is, or length squared. So you just take the inner product. So we take the complex conjugate version of this. That's that guy. That's the regular vector plus, that's that one. And if we just multiply each of these out, let me get the pen. Okay, here we go. We multiply each of these terms out. So here's 0 and 0. This will give like a 1 here. 1 and 1. This will also give 1. The 0 and the 1 combination will give 0. And the 1 and the 0 will also give 0. So this thing would actually be equal to 1/2 of basically 1 plus 1 plus 0 plus 0. Well, these are the four terms when you expand this. And so 1 plus 1 divided by 2 is 1. Okay, so it's normalized. Okay, what about the orthogonality? So we want this plus and minus to be orthogonal to each other. So here we've stuck in the minus state here, and here's the plus state. All right, so we basically do the same thing. It's just about the same thing, but we have an extra minus here. So in this case, what's going to happen is that the 0, 0 combination will give 1, but then the 1 and 1 combination here will give -1. And then the other one's 0 as it was before. And so this is 0 because 1 minus 1 is 0. Okay, so these are orthogonal. So, I mean, and you can just tell that they're orthogonal just by looking at this picture, right? Okay, so now let's rewrite the state in terms of the plus and the minus. Okay, so how do we do that? Well, so we've got the definitions of the plus and the minus, but in order to convert our original state, which was written like this, we need we need to kind of invert this equation here so that it's like 0 is equal to plus minus something or other, and 1 is equal to plus minus something or other. This is sort of it's going the wrong way. It's telling us what plus is in terms of 0 and 1, but what we want is we want to know what like 0 is in terms of plus and minus. So how do you do that? Well, basically what you do is just manipulate these equations so that you kind of cancel. It's just like, you know, what you do in algebra. So you add and subtract the equations so that you kind of get the term that you want. So for example, if you add these two equations, so if you just add them, so then this term and this term, the zeros, so on the right hand side, the zeros will just give, um, uh, uh, okay, so right, so let's just do up here. So 0 plus, we're going to add these two equations. So what's going to happen is that, okay, we've got this 1 over square root of 2 factor here. But we've got 0 and 2 zeros, so we're going to get 2 zeros, and then this 1 and the -1 will cancel, so that will not be there, and we've got 2 divided by square root of 2, so that's actually square root of 2 multiplied by 0. And then if you just rearrange this, put this square root of 2 on the other side, then you get this equation. Okay, So now we know how to write the 0 in terms of plus and minus. Now if you subtract these two equations, you basically get the same thing. Instead of the 1 cancelling, the zeros cancel because it's like 0 minus 0. And then you get an equation for 1, and then you get this one. Okay, once we've got that, then it's easy. You just substitute this thing into that equation. So just go ahead and do that. Then you get alpha 1 over square root of 2 of plus state plus minus state. And here we get beta 1 over square root of 2 and plus state minus state. Okay, then if you rearrange this, so just collect the terms, we've got a plus and plus here, we can just factorize this. We've got alpha plus beta over square root of 2, and you got this term, and here you got alpha minus beta, and you got the second term. So we can just read off the coefficients now. So for example, here we've got the coefficient of the plus state is just simply this number here. The coefficient of the minus state is just this number here. So that's how we can rearrange the equations in terms of the new basis vectors. Now, that was just basically an example. I just more or less chose that transformation here. So this is Bob's choice of how to represent the state. That was just, I could have chosen a different example. A more general way of choosing two orthogonal states is basically what I talk about in this slide, right? So the most general pair of orthogonal states. So what we need to do is we need to make sure that these two states chosen by Bob, the red ones, they need to be at right angles to each other, right? So they need to be right angles. They also, each vector needs to be kind of length 1, right? Because they're supposed to be basis vectors, and we want them to be length 1. So how do we do that? Well, actually, this is simple. For qubits, it's actually a simple way to choose this. So we can actually just choose any kind of alpha and beta first for the first state, 0, and we have to make sure it's normalized. Otherwise, this thing won't be normalized. Then we can find the state which is orthogonal to that just by this simple formula, because and it basically goes as like you just swap the alpha and the beta, and then you take the complex conjugate, and then it gives you a state which is always orthogonal to the 0 state. So 0 and 1 are always orthogonal. Okay. How does that work? Well, we can just prove it to ourselves and show that it really is orthogonal. So firstly, let's look at the normalization of 0. So this is kind of already obvious from what we discussed before. So for example, if you just substitute here and look at these coefficients, then for example, this term and this term gives you the alpha squared. This term and this term gives you the beta squared. So those two terms, by definition, go to 1. The orthogonality is maybe the more interesting thing here. So let's just take the inner product of 0 and 1. Okay, so that's that. We've got beta and alpha, and this is the original vector. So the conjugate vector is the thing that you need to take the complex conjugate of, and then flip the directions of the vectors. So it's beta 0 and then minus 1. Okay, this is the original vector for 0, and again we only have to look at the terms that are going to give you know an inner product equal to 1. So for example, this term, so it's 0 and 0, and here 1 and 1. The other terms like 0 with 1 or 1 with 0 are always going to give 0. So this term here gives beta alpha, So this is equal to beta alpha. And this term here gives minus alpha beta. Okay. And so that's obviously equal to 0. So these are always orthogonal. So that's a more general way of writing orthogonal vectors. So let's just do a kind of a simple example, just play around with this. So previously let me put myself here. So previously I also said that actually a kind of a neat way to parameterize the the normalized states was this cosine and sine kind of way of writing this. This way is neat because you don't have to worry about the normalization. This kind of the trigonometric relations kind of guarantee that this is always normalized, right? Okay, so let's just go through a couple of these questions. So what is the orthogonal vector 1? So we just basically follow this formula on the previous page. So what we need to do to get the orthogonal vector is to kind of swap these, put a complex conjugate on it, and then put also a minus sign here. Okay. So in this case, the 1 beta, the orthogonal state, okay, so we need to swap it, put complex conjugate, and then put a minus sign, okay? So this is going to be minus I theta sine of theta over 2 and cosine theta over 2 1. And these are all like Alice's versions of 0 and 1. Okay, so that's it. So that's, swap, complex conjugate, it's got a minus there, it's supposed to be an I there, and a minus sign here. Okay, so that is just that. I'm just following the formula on the previous page, and we know that works. Okay, show that the vectors are orthogonal. All right, fine. So, let's calculate 0 and 1 for Bob states. Okay. All right, so we need to take this term, and then we need to firstly make the conjugate vector. So notice I need to do the minus of the e to the I phi here because I'm taking the conjugate vector. And then I just have to just copy this one here. Okay. Now I need to take the inner product of these two. So this pair, so this 0, 0 will give something non-zero. So this term is going to give cosine of theta over 2 times this stuff here. So e to the minus I phi of sine theta over 2. And then I need to do the inner product of this pair here. This is the 1 and the 1. So this one is e to the minus I phi times by sine theta over 2 and cosine of theta over 2. And so we've got exactly the same terms here, and of course all the other cross terms are all 0. So cosine theta over 2, either minus I phi sine theta over 2 minus, e to the minus I phi sine theta over 2 cos theta over 2, so this is exactly equal to 0. So this shows that these are orthogonal. Now, finally, what are the vectors 0, 1 in terms of uh, 0, 1 out in terms of Alice's vectors, in terms of 0, 1 in terms of Bob's vectors. Okay, so what we need to do here is we actually need to multiply, basically add and subtract these types of equations so that it gives the same kind of the inverted relations. So here's our two equations here. Okay, and so what we want to do, how do you get these factors here to cancel? What we need to do is actually multiply by some factor on this equation and multiply this equation by some factor so that these two terms cancel here, right? Okay, so let's do this for to get, say, the first equation. So first, let's multiply the first equation 0b by a factor of e to the minus I phi sine theta over 2 of 0b. And let's also multiply by the second equation by a factor of cosine theta over 2. Like this. And if we do that, then what we're going to get is, so we get this e to the minus I phi sine theta over 2. This is cosine theta over 2 on 0. And we multiply this term here by whatever factor we've multiplied here by. And what we're going to get, the e to the I phi's are going to cancel, and we're going to get sine squared of theta over 2, 1. For the second term, so let's multiply this term by this cosine theta over 2. Okay, so it's cosine theta over 2 e to the minus I phi. And over here we've got minus cosine squared theta over 2. Okay, now notice that this term here is exactly the same as this term here. So if we just subtract these two terms, then what's going to happen is that these terms are going to be these terms will cancel, and then you'll get sine squared minus minus cosine squared, and that will be equal to 1. Okay, so these are all Alice's vectors, right? Alice's vectors. So let's just subtract this equation. So let's just subtract 1 minus 2. So what we're going to get is e to the minus I phi of sine theta over 2 of 0b and just subtracting it, we're going to get is these terms cancel, and it's going to be sine squared plus cosine squared, which is just going to give 1, and this gives our relation 1 in terms of alpha, in terms of Bob's vectors. Now, so you can do basically the same steps to actually eliminate um, uh, 1 from these two equations, what you need to do is here to multiply by cosine theta over 2, and over here multiply by e to the I phi sine theta over 2, then add the equations, then what you should find is that you can invert these relations too. Okay, so I think you can maybe try and work the second vector out in terms for yourself, and we can leave it there. Um, as usual, please go and try and do the homework questions. There are some extra problems, I think, on linear algebra that you should do, and I will speak to you next week. All right, see you later. Bye.